1,962 commercial vessels sit at anchor. They do not move. The geographic coordinates locate them just outside the Strait of Hormuz. The waterway remains closed for 27 consecutive days. Brent crude trades at $126 per barrel, a four-year peak. Exactly 20 million barrels of crude oil fail to transit every 24 hours. One-fifth of the global supply chain halts. This disruption includes fertilizers, plastics, and pharmaceutical precursors. Every modern industrial process requires input from this specific geographical choke point. Before the conflict, 138 vessels transited this exact coordinate every 24 hours. Today, satellite AIS tracking registers 16. 8 of those operate as dark ships. They run without active transponders. Iran permits exactly 5 nations to pass: China, Russia, India, Iraq, and Pakistan. The rest of the global fleet waits. Our insurance premiums for a single supertanker transit currently stand at over $1 million. The mathematical reality of these risk models forces a maritime standstill. The United States Pentagon initiates a 3-phase operational plan. Phase 1, degrade launch capabilities. Phase 2, neutralize the subsea mine threat. Phase 3, escort commercial tonnage. Phase 1 approaches completion. Phase 2 presents an extreme engineering bottleneck. The strait measures exactly 34 kilometers wide at its narrowest point. Traffic separates into 2 primary shipping lanes. Each lane spans 3 kilometers across. A 3-kilometer buffer zone divides them. Every vessel must navigate through Iranian territorial waters near Larak Island. The bathymetric profile reveals an average depth between 60 and 100 meters. This specific vertical column is deep enough to conceal a subsea device. It is shallow enough for an explosive payload to maintain lethal kinetic energy upon reaching the surface. The seabed consists of flat sand and heavy silt. This geologic composition creates the optimal environment for synthetic anomalies to disappear. The primary engineering challenge lies beneath the surface. Iranian forces deployed a portion of their 6,000 to 8,000 naval mines. Intelligence confirms at least 21 merchant ship attacks and 12 active devices located in the primary transit lanes. This is the Maham 3, a moored configuration. It utilizes dual-threshold magnetic and acoustic sensors. It maintains buoyancy several meters below the waterline. A standard very large crude carrier displaces over 300,000 tons. This massive concentration of steel distorts the Earth's local magnetic field. The Maham 3's induction coils detect this micro-Tesla shift. When the magnetic threshold is breached, the firing circuit completes. This is the Maham 7, a bottom-resting limpet mine. Engineers designed its composite outer shell specifically to scatter incoming acoustic sonar waves. It buries itself in the silt. It remains virtually undetectable until the pressure wave of a passing hull triggers the hydroacoustic detonation sequence. This is the EM-52, a rocket-propelled ascending mine. It rests flat on the seabed. When its passive acoustic sensors detect the specific frequency of a commercial propeller shaft, it ignites a solid-fuel rocket motor. The propellant remains stable underwater for months without chemical degradation. The hydrodynamic profile of the ascending warhead minimizes water drag. It targets the weakest structural point of a vessel's hull from directly below, a weapon system that hunts the ship. Clearing this environment requires specialized hardware that no longer exists in the region. In January 2026, the United States Navy decommissioned its last 4 dedicated mine countermeasures vessels in the Middle East: the USS Devastator, the USS Dexterous, the USS Gladiator, the USS Sentry. These Avenger-class ships utilized wooden hulls coated in fiberglass. This specific material science choice prevented the triggering of magnetic sensors. They successfully neutralized over 1,000 mines during previous operations. Heavy lift transport vessels moved all 4 units to Philadelphia for disposal. 30 years of operational service terminated, and their replacements arrive. 3 Independence-class littoral combat ships, the USS Canberra, the USS Tulsa, the USS Santa Barbara, They feature an aluminum trimaran hull design. They do not sweep for mines directly. They act as motherships for the mine countermeasures mission package. This system relies on unmanned surface vehicles, MH-60S Seahawk helicopters, and expendable underwater drones. The technology represents a complete paradigm shift in naval engineering. It isolates human operators from the blast radius. However, the system lacks extensive combat verification. The Pentagon's Operational Testing Directorate cited insufficient data to confirm its effectiveness in a contested environment. The unmanned surface vehicles operate on high-bandwidth line-of-sight data links, and this physical limitation requires the aluminum-hulled mothership to position itself near or directly inside the active minefield. Aluminum does not absorb blast overpressure like high-yield steel. Furthermore, the system relies on mechanical deployment. A single mechanical failure in the launch crane or a hydraulic fault in the platform lift halts the entire operation. UK Defense Secretary John Healey confirmed the reality on March 11th. Mine clearance is near impossible during active conflict, but the global economy cannot wait. The mine countermeasures operation initiates Phase 2. A coalition force assembles in the Gulf of Oman. 3 Independence-class littoral combat ships position themselves near the 34-kilometer entrance of the strait. This operation requires the meticulous scanning of every square meter across a 6-kilometer-wide shipping corridor. It is not a broad sweep. It is a high-resolution subsea forensic examination. The primary airborne platform, the MH-60S Seahawk, deploys from the flight deck. It carries the AN/AES-1 Airborne Laser Mine Detection System, ALMDS. This system addresses the near-surface and floating mine threats. The helicopter flies a precise grid pattern at low altitude. The ALMDS pod projects a pulsed laser beam directly into the water column. The system utilizes light detection and ranging, LiDAR technology. The laser pulses penetrate the surface and reflect off suspended objects. The pod's streak tube imaging LiDAR receiver captures these reflections. The onboard processor analyzes the return time of the light pulses to generate a 3D topographical map of the upper water layer in real time. It operates continuously, calculating the precise depth and shape of any anomaly large enough to be a Maham 3 moored mine. However, the laser cannot penetrate deep enough to locate the seabed threats. This requires direct acoustic scanning. The USS Santa Barbara launches its unmanned surface vehicle, USV. The crane lowers the 12-meter semi-autonomous craft into the water. The USV's primary function is to act as a towing platform for the AN/AQS-20C mine hunting sonar system. The USV unspools a reinforced tow cable, deploying the sonar array approximately 200 meters behind and below the vessel. The AN/AQS-20C is a wideband, forward-looking side scan and volume search sonar. So as it glides above the seabed, it emits high-frequency acoustic pulses. These sound waves travel through the water, strike the ocean floor, and bounce back. The system's receiver arrays capture the returning acoustic energy. The varying intensities and return times of these echoes create a high-resolution photographic quality image of the topography. The system is sensitive enough to detect the specific geometric shape of an EM-52 cylindrical casing or the subtle dome of a Maham 7 limpet mine. The raw acoustic data transmits back to the LCS mothership via a high-bandwidth radio frequency link. On board the USS Santa Barbara, sonar operators analyze the incoming telemetry. This is where the extreme engineering bottleneck occurs. The Persian Gulf seabed is not a sterile environment. It is a highly cluttered, industrialized zone. Our decades of commercial shipping, regional conflicts, and fishing operations have deposited thousands of metallic objects onto the sand and silt. Shipping containers, discarded engine blocks, wrecked hulls, and industrial debris litter the transit lanes. Every single object larger than a 50-centimeter diameter registers as an anomaly on the sonar screen. The system flags it. The human operator must manually classify it. The statistical probability dictates that for every actual explosive device, the sonar array detects hundreds of false contacts. The Maham 7 is explicitly designed to mimic the acoustic profile of a submerged rock. It possesses a low radar cross-section and a non-cylindrical, irregular shape. Furthermore, the tidal currents constantly shift the silt, burying and unburying these objects, altering their acoustic signatures. The operators must halt the USV's forward progress to investigate every ambiguous contact. This process drastically reduces the sweeping speed. The 34-kilometer transit lane must be verified meter by meter. When the sonar operators classify a high-probability target, the neutralization sequence begins. The LCS cannot simply detonate the mine with artillery. The explosive shockwave could trigger sympathetic detonations in nearby undetected mines or damage the fragile subsea infrastructure of nearby pipelines. The neutralization must be surgical. The MH-60S Seahawk returns to the contact coordinates. It hovers directly over the target zone. It deploys the AN/ASQ-235 Airborne Mine Neutralization System, AMNS. The helicopter lowers a deployment pod into the water. This pod contains 4 expendable, wire-guided unmanned underwater vehicles, UUVs. The operator in the helicopter's cabin pilots the UUV via a fiber optic tether, utilizing the drone's onboard forward-looking sonar and underwater video camera. The UUV descends through the water column. It must navigate the strong subsurface currents of the strait to reach the target. Upon visual confirmation of the mine casing, the operator maneuvers the UUV to within centimeters of the device. The UUV is essentially a highly maneuverable shaped charge. It attaches itself to the mine or hovers immediately adjacent to the primary explosive payload. Once the drone is locked in position, the helicopter retracts the deployment pod and ascends to a safe standoff altitude. The operator transmits the detonation signal through the fiber optic cable. The UUV's shaped charge detonates. The focused explosive jet penetrates the mine's casing, destroying the firing mechanism and initiating a low-order detonation of the main charge. The threat is neutralized. The UUV is destroyed in the process. This intricate, multi-stage robotic sequence must be repeated for every single confirmed contact across the 34-kilometer strait. It is a painstaking, methodical procedure occurring in a highly contested combat zone. The mathematical reality of this operation dictates the global economic timeline. Every 24 hours, the strait remains closed. The cumulative shortfall of crude oil increases by 20 million barrels. Gulf nations have already enacted emergency production cuts exceeding 11 million barrels per day to prevent storage facilities from overflowing. The International Energy Agency has initiated the largest coordinated release of strategic petroleum reserves in history. Kuwait possesses exactly 14 days of domestic storage capacity. Once that capacity is reached, their extraction operations must shut down entirely. Energy analysts project a global shortfall of between 630 and 1,080 million barrels over a 3-month period. The subsea clearance operation cannot operate on a timescale of months. Yet naval engineering models indicate a minimum of 4 to 6 months to achieve a 99% clearance rate in a contested environment with an active threat of remining. The time required to scan, classify, and neutralize simply exceeds the global economy's capacity to absorb the disruption. The world requires a faster, albeit more dangerous, solution. Phase 3 initiates before Phase 2 completes. The global economy cannot wait for a 34-kilometer sterile corridor. The coalition forces pivot to a high-risk operational doctrine. Operation Earnest Will 2.0 commences. In 1987, the United States Navy escorted 11 Kuwaiti tankers through this identical geographical choke point over a 14-month period. That operation faced contact mines and small attack craft. The 2026 operational environment is exponentially more lethal. The threat matrix now includes rocket-propelled subsea munitions, anti-ship cruise missiles, explosive loitering munitions, and shore-based radar-guided systems concealed within hundreds of kilometers of fortified coastal caves. The coalition establishes a partially cleared corridor, a 6-kilometer path verified as temporarily mine-free. It is insufficient for high-volume commercial traffic, but it establishes a tactical proof of concept. A convoy assembles in the Gulf of Oman, two very large crude carriers, VLCCs. The escort architecture is absolute. One Arleigh Burke-class guided missile destroyer positions itself at the vanguard. A second destroyer secures the rear. The destroyers operate the Aegis combat system. This integrated naval weapon system utilizes the Spy-1 passive electronically scanned array radar. It tracks every airborne and surface contact within a 300-kilometer radius simultaneously. It processes the kinematic data of incoming threats and automatically assigns the optimal interceptor missile. The convoy proceeds at exactly 8 knots. This is the maximum operational speed for the forward-deployed unmanned surface vehicles, towing the AN/AQS-20C sonar arrays. And they must continuously sweep the water directly ahead of the lead destroyer to ensure the corridor has not been remined. Above the convoy, MH-60S helicopters fly advanced patterns, utilizing the ALMDS laser system to scan for floating contact mines. At 8 knots, transiting the 34-kilometer strait requires over 2 hours of continuous exposure, 2 hours within the engagement envelope of Iranian anti-ship batteries. The defense is multi-layered. If a shore-based battery launches a cruise missile, the Aegis system detects the launch plume. It calculates the intercept trajectory and fires an SM-2 standard missile. If the intercept fails, the ship's secondary defenses engage. The CRAM system launches a rolling airframe missile to destroy the threat at medium range. If the threat penetrates the inner perimeter, the Phalanx Close-In Weapon System, CIWS, activates. This radar-guided 20mm Gatling gun tracks the incoming missile and fires 4,500 armor-piercing tungsten rounds per minute, creating a kinetic wall of depleted uranium or tungsten to shred the warhead in the final seconds before impact. Simultaneously, the destroyers deploy chaff to confuse radar seekers and infrared flares to decoy heat-seeking munitions. Electronic warfare suites jam the targeting frequencies of the IRGC command centers. Above the convoy, F/A-18. Super Hornets from a distant carrier strike group provide continuous combat air patrol. On the flanks, fast patrol boats monitor for IRGC swarm tactics. The convoy operates as a heavily armed floating fortress. However, the mathematics of this operation remain unsustainable. The Pentagon's tactical doctrine dictates a ratio of 1 destroyer for every 2 commercial tankers. The United States currently maintains 14 destroyers in the Central Command area of responsibility. 6 of those vessels are dedicated to protecting the aircraft carriers. This leaves 8 destroyers available for escort duties. This allows a maximum throughput of 4 tankers simultaneously. Reaching the pre-conflict volume of 20 million barrels per day requires the transit of hundreds of tankers. The military escort capacity simply cannot meet the commercial demand. Simultaneously, alternative infrastructure operates at absolute maximum physical capacity. The terrestrial bypass system. Saudi Arabia activates the east-west crude oil pipeline. This 1,200-kilometer engineering marvel stretches from the Abqaiq processing facility to the Yanbu terminal on the Red Sea. Its design capacity is 7 million barrels per day. Prior to the conflict, it operated at 770,000 barrels. Engineers have rapidly pressurized the system, increasing flow to 2.9 million barrels per day. The hydraulic pumps are operating near their structural limits. The United Arab Emirates utilizes the Abu Dhabi Crude Oil Pipeline, ADCOP. This system transports oil from the Habshan onshore field directly to the Fujairah terminal on the Gulf of Oman, physically bypassing the Strait of Hormuz entirely. Its maximum flow rate is 1.5 million barrels per day. It connects directly to the Al Mandus underground storage facility, a massive subterranean cavern capable of holding 42 million barrels of crude. Iraq maximizes the Kirkuk-Ceyhan pipeline, moving crude to Turkey's Mediterranean coast. Its capacity is 1.6 million barrels per day, though it currently operates at 200,000. Combining these terrestrial routes yields a maximum theoretical bypass capacity of 5.5 million barrels per day. The Strait of Hormuz normally handles 20 million. The permanent, unbridgeable gap remains 14.5 million barrels every single day. To mitigate the risk of a catastrophic blockage within the cleared corridor, the coalition implements a militarized vessel traffic management system. They install 800 high-definition optical and thermal cameras along the coastlines. Every meter of the 6-kilometer channel is monitored in real time from a centralized command center in Bahrain. The protocol mirrors the Panama Canal's strict scheduling, but adapted for an active war zone. A supertanker fire in this confined space is the ultimate nightmare scenario. Emergency response tugs are stationed every 5 kilometers, while the 60 to 100 meter depth means a sunken VLCC would not physically block the entire strait. The resulting environmental disaster and the complex salvage operation would halt all transit for weeks. Every movement is calculated, every variable is measured. Slowly, the cleared corridor expands. 6 kilometers becomes 12, 12 becomes the full 34-kilometer width. The convoys increase in size. The global markets react instantly to the flow of crude. Brent crude prices drop from the $126 peak. The insurance premiums stabilize, but the fundamental reality of global energy infrastructure remains unchanged. The naval destroyers must maintain their patrols. The unmanned surface vehicles must continuously scan the seabed. The coalition must maintain a permanent high-readiness presence. As long as 20% of the world's oil flows through a single 34-kilometer gap, controlled by the coastline of a single nation, the vulnerability is permanent. No pipeline network, no terrestrial bypass, no alternative maritime route can fully replace the sheer volume of the Strait of Hormuz. It remains the most strategic and currently the most dangerous waterway on Earth. The engineering operation to keep it open is continuous, and it is happening right now. This video is a conceptual simulation of military operations based entirely on publicly available data from the IEA U.S. Naval Institute, Congressional Research Service, Naval News, CNBC, and verified media reports as of March 28, 2026. It does not represent classified military plans or operations. All visuals are AI-generated simulations, clearly labeled per YouTube's disclosure requirements. The actual operation to reopen the Strait of Hormuz is ongoing. Subscribe to Hormuz Decoded to follow what happens next.